So yeah, I wanted to give a tutorial on auto precompiles from the lens of an application developer. So I assume most of you are familiar with zkVMs and also the concept of a precompile in that context. So a zkVM precompile is basically a zk circuit that proves a specific function, let's say a hash function, and usually they're written by experts. And if you're writing an application and you happen to do some computation that has a precompile, that's great because that means the proving is a lot faster. But what happens if there's no precompile for the computation? Then either you have to make one, which is it's a lot of work, it takes a lot of auditing effort, there's security risks, or you can use auto precompiles. So let's talk about an example application. So let's say your application is that you want to prove that you've edited some image. Let's say you've blurred some image. Why would you want to do it? Because maybe the input image is signed. Maybe it comes from an attested sensor or some camera that signs the image. But the problem with that is that once you apply the blurring, then you lose the signature, because the signature only signs the input image but not the output image. But if you prove this transformation, then you can establish a link between the input and the output, and you can basically say that this is an authentic image, it's not AI generated or anything. And I've applied a blur to it, but apart from this, there's nothing else. And in particular, I didn't just make up a new image. And so the idea here is very simple. We write a Rust program that blurs an image, and then we prove it using OpenVM. OpenVM is just one of the many RISC-V zkVMs. One advantage is it has integration with auto precompiles, so that's going to be convenient. So this is the Rust code. So the first few lines are just receiving the image as private input to the zk proof. And then we hash the input, we blur it, and we hash the output. And in the last block, we publish the two hashes as public outputs of the zk proof. And so again, this establishes a link between the two hashes, basically proving that they correspond to two images, and the relationship between them is that one is a blurred version of the input image. And the main proving time will be spent here because this is where we actually process the image data, which is relatively large amount of data. And if we zoom in more closely, what we'll find is that hashing, which is an expensive operation, but proving it is actually relatively cheap, and that's because OpenVM ships with a Ketchak precompile. But the blurring operation, it doesn't have a precompile, so that's what's taking up most of the prover resources. So let's dive in more deeply, like how does the blurring work? In this example, I chose a very simple blurring algorithm, just like a sliding window over the image, and then every time there's a window, it averages all the pixel values, and that average becomes an output pixel. This is the same in Rust code. So the two outer loops, they loop over all the pixels on the image, and the inner loops, they loop over the pixels on the window. You can see I already did some trickery, some Rust trickery to make it more efficient. So I used a macro to unroll these inner loops, and I also used some unsafe Rust to get rid of some range checks. And the result of this is that this block here, it doesn't have any control flow. There's no dynamic loops. There's no conditional branching or anything like this. And that makes it very suitable to be turned into a circuit. And that's what auto precompiles do. So let's have a brief look into how this works under the hood. So we start out with some zkVM, in this case OpenVM. And you can think of a zkVM as just a collection of zk circuits. For example, there could be one for each RISC-V instruction. And then we have a basic block. It could be the one that I just showed on the previous slide. And it's just a list of instructions, consecutive instructions in the program, and only the last instruction can be a branching instruction. And what we want is a zk circuit that proves the execution of this basic block in one go. So we start out by just copy pasting together whatever circuits would have been used by the zkVM if it didn't have a precompile. And then we have one monolithic circuit to prove the whole block. And then we run a circuit optimizer to make it smaller. And this is where the magic happens and where we see the gains. And I would say typically in this optimization step, we see a factor 3 to 4 improving time improvement for the specific basic block. But it can also go higher. Like we also see examples where it's more than 10, but like 3 to 4 is a very common factor. And this is the result. So if we look at trace cells, so trace cells is the data that the prover has to commit to when creating the proof, and it's one of the main costs of proving something. And the pie charts here, they show the distribution over the chips in the zkVM. And I just want to highlight two things. One is the catch-up precompile. So on the left side, we see the distribution without auto precompiles. And we see that the catch-up precompile, which does the hashing, only takes up about 20% of the resources. So that's what I said earlier, that the hashing is actually relatively cheap. And most of the other chips are busy proving the blurring. And then after auto precompile, the absolute numbers of the catch-up precompile, they stay the same. But because everything else shrinks, the share goes up to 55%. So actually, after auto precompiles, the majority of the prover work is to prove the hashing. And you can see that's a bit over 30% of the prover work goes into the auto precompiles that we added, and then there's like a few smaller chips left. And so the reduction in trace cells is 2.9 in this example, and this translates to proving time, reducing the time by a factor of 2.4 in this example. So on my laptop, it took about like a bit over a minute to prove the blurring of this Ethereum logo that I showed before. And now it's under 30 seconds. One interesting thing you can see in this chart is this. It shows the total proving time, but it also splits it down to the different phases. And OpenVM just doesn't just create one proof, it also recursively aggregates proofs and shrinks the proof. And you can see that the recursion step, which is the yellow part here, actually becomes a little bit larger. And that's because there's a cost to adding more chips to a zkVM. But it's a relatively small cost, and because aggregation is fast in general, there's still an end-to-end improvement. These were my slides. Yeah, any questions?